So good afternoon. So we have the pleasure to welcome Emma Curtis-Lake, who will tell you about distant galaxies with James Webb. Thank you, Emma.
Hello, everyone. It's so nice to finally be here. I've met a few of you already with the practical hands-on, and I really hope you're enjoying this school so far. I'm going to start off with your observations section with distant galaxies with JWST. These are probably much more distant than most of you had dealt with. Just to give you an idea, for me, intermediate redshift is 4 to 7. High redshift, yeah, sure. Above redshift 11, you're getting to high redshift. So I didn't manage to give you a lightning slide, so I'll just quickly introduce myself. So I'm a Webb Fellow in the UK. There's like 3 of these fellowships. And it's about doing science with JWST, supporting the community in using the telescope, and also trying to take the public along for the incredible journey. I'm the PI of the near-spec side of the JADE survey. And this is the largest survey with JWST in the first 2 years of operations. I'm going to be showing you some cool results from that survey. I'm currently lead developer of an SED fitting code called Beagle and Beagle AGN, and some people have been having fun with that already this week. And things I love, just in a random order, certainly not this order: statistics, galaxies, my family, gardening, reading, traveling, talking to the public about this telescope, working with students, and anything about the early universe. I'm definitely like an astronomy geek at this level, and it's fun to be doing this job, right? So in terms of this talk outline, I'm going to give you some very broad brushstrokes about how we investigate galaxy evolution. I'll talk a little bit about how we were inferring galaxy properties of distant galaxies pre-JWST, and I'm kind of thinking of what I termed intermediate redshifts, so pretty high redshifts. And then how this got transformed when we had NearCam available. There's a lot more information from the range of filters that we can use on a telescope. There's MIRI, there's spectroscopy. I'm going to give you a little introduction to SED fitting because some of the results revolve around that. And then early galaxy evolution should be easy with JWST now, right? So we'll look at some results and how it's going. At certain points between those sections, I'll just pause, see if there's any questions. So we won't just be in one long, one long talk from me. Galaxy evolution. I'm going to start with the whole history of the universe in a single slide. Maybe some of you aren't sick of this slide if you haven't worked at high redshift, but every talk I give, this slide has to be in it. We start 13.8 billion years ago with the Big Bang. After a certain amount of time, the universe has expanded and cooled enough that we get neutral, normal atoms out of the primordial soup of particles, and it's predominantly hydrogen, helium, smatterings of lithium and beryllium. And then we enter what's called the dark ages. There is actually light, it's not completely dark. There's light left over from the last scattering surface, or the CMB, which is rapidly cooling, rapidly moving to longer wavelengths. There's also some light from neutral hydrogen. It has some rotational modes and 21 centimeter emission. But there's no stars there. There's nothing emitting stuff in the optical, in the UV, or anything like that. So we call it the dark ages, and it takes a while for things to get going because it takes a little while for gravity to be doing its job. From initial fluctuations, slightly denser regions will be getting denser and denser as it pulls matter into them. And you have to get enough matter, enough density, the perfect conditions to be able to ignite hydrogen fusion and form your very first population of stars. And we think that they're really different from the stars in the local universe, probably really big. And there's a simple sort of explanation for this. When you've got a gas cloud, collapsing, the routes for the energy to escape is usually through things like atomic transitions and emission lines or rotational modes from complex molecules. They make energy easy to escape. The cloud can collapse, fragment, you can form lots of different stars, different masses. You've only got neutral hydrogen, helium. There's not many modes for escape. We think we have, in the end, massive stars, maybe like 500 suns worth. They die quickly, and if they die as a supernova, or even in their lives, if they have strong stellar winds, they're spewing out the products of stellar nuclear synthesis into the surrounding interstellar medium. So pretty cool epoch to investigate. Maybe we learn about the very first stars. Maybe we'll even find some. And then, yeah, lots of stuff happens. We have hierarchical structure formation. We have huge clusters of galaxies that form over time. But this talk, we're going to talk more about the sort of early days or early years of galaxy formation. What might we expect to be evolving in the galaxy population? We can even go very simple, right? We hope that there's a buildup in the number of galaxies over time. We start from 0, we have tons today, we've got to see the buildup. How do they build up? That's probably where the interesting physics is, right? They're going to be getting more massive in terms of their stars, because they'll be forming stars as they go. There'll be mergers and all these other processes. We're going to see the amount of metals in their interstellar medium changing as successive populations of stars form and spew out those metals into the ISM, and other processes happening. We'll probably see depletion of the gas reservoirs as that fuel gets used up to make stars. And then there's all these other amazing things like the prevalence of AGN and other exotic stuff going on. How do we study galaxy evolution? Well, at the highest redshifts, it's been quite simple. And this broadly applies to lower redshifts as well. It's just that the complexity gets so much greater, so much quickly. But you can think of taking some populations of galaxies, measuring their properties. These could be just simple properties, even like brightness, mass, amount of metals, plotting some against the other, looking at how they evolve. You hope you've got some physical intuition as to why they're evolving, and you hope you have them reproduced in some galaxy simulations, and then you can really start to interpret your physical processes. But in essence, this is where you can start. And one property that sort of describes a little bit of how the galaxy population evolves in time has been taken from counting galaxies, trying to estimate their star formation rates in various ways, and estimating the density of star formation in a co-moving megaparsec with cosmic time. And what we see is that it increases at the beginnings. That's that buildup of galaxies, right? It's imprinted in this. Keeps increasing, so our gas reservoirs are probably fueling the star formation in these galaxies. We get to around cosmic noon, around redshift 2 to 1, and things change. And it starts to decrease and decline. The sites of active star formation tend to be in lower mass galaxies. The higher mass ones have either heated up the gas too much that they can no longer access it, or have run through their fuel. So counting galaxies, that's one of the first things we do at high redshift, honestly. Here's a luminosity function measuring the rest frame ultraviolet. So we have increasing brightness in this direction. This flips around, I'm sorry for that. Different plots will have it in different directions. And then we're essentially counting the numbers of galaxies of a given brightness within a survey volume. That cosmic star formation rate density measure, some of the simple estimates have basically taken the UV luminosity, mapped that to a star formation rate, integrated your UV luminosity function down to a certain point, And then you see that what's happening is as the galaxy number density increases, as your population of galaxies is increasing from the very beginning, you end up with that increasing cosmic star formation rate density or increasing density of galaxies at a given UV luminosity with decreasing redshift. So it's just easy to see at the simple level. Before JWST, we weren't really sure about what was happening at the very early times. So this is back to the cosmic star formation rate density plot, flipped on the axis. Sorry for that. I would have flipped these over for you or flipped the other one. It was just going to be too complicated. For pre-JWST, they're saying, okay, well, look, dark matter halos are evolving really rapidly at these high redshifts. And we are noticing from the galaxy population that they are roughly following that number density. So that rapid increase in the number densities of certain halo masses is being replicated in the galaxy population. But another group said, no, we don't agree. This was pre-JWST. So we had a bit of a redshift frontier going on as well. Hubble could see to within around 400 million years after the Big Bang. JWST looks in the infrared. It can see further. It can see to higher redshifts. So we hope that we can see to the very beginnings of galaxy formation and also probably figure out what's happening with that rising cosmic star formation rate density. But also at lower redshifts, we can do much more interesting things. There's the well-known relationship between stellar mass and gas phase oxygen abundance in the ISM. So this is the mass metallicity relation at low redshifts. So lower mass galaxies have lower metallicities. And then even from there, there's been suggested that this is dependent on the star formation rate of the galaxies, such that if you increase the star formation rate, the metallicity will be lower. So some possibilities there is that if you've got infall of low metallicity gas onto your galaxies, it can boost your star formation in that galaxy, but also lower the metallicity. This has been looked at to higher redshifts, pre-JWST, strong evolution in the mass metallicity relation, but we were completely limited because we couldn't go to high redshifts because we couldn't access the rest frame optical from the ground. The atmosphere gets in the way. So with JWST, all of this initial period now is unlocked because we get to take spectra of galaxies up into the rest optical from, I didn't explain what the epoch of reionization is, but there's a period of time through which the neutral hydrogen becomes ionized by the sources in your universe. And so we can assess all of these things right up well within the epoch of reionization, thanks to the spectroscopy. Oh, sorry. The reason I'm telling you quite a lot about pre-JWST is because it kind of impacts what we're learning now and why we're learning slower. So I want to tell you a little bit about how we were inferring galaxy properties before we had spectra, before we had NearCam, before we had all of the beautiful images that JWST would provide. And in terms of high redshift studies, the timeline starts at around 1996, the first spectroscopic confirmation of objects around redshift 3 using Lyman break technique, which I'm going to explain. 2002 is the beginning of a Hubble imaging survey across 2 deep fields, the Good South and the Good North. So these are fields which have had tons of multi-wavelength exposure from X-rays to radio. And some people are using data from them at this minute. I asked, how many of you heard of these deep fields? So I wanted to put this in. September 2003 to 2004, the director of STSCI said, you know what, I want to take tons of Hubble time and sit on one patch and stare at it and see what happens. And people were saying, some people were saying, I think this is crazy, you're going to run out of galaxies. Sat there for 11 days and produced the first image of the Hubble Ultra Deep Field with thousands of galaxies in it. In 2009, Hubble was upgraded with a more sensitive infrared camera. Now people could search for galaxies to a redshift frontier of 11 to 12. There was more imaging put into this, but progress was slow on other means. We had candidates. Very few could we get spectra of. Sometimes we could get spectra with ALMA, but really we were kind of stalled and waiting for JWST. So this is that gorgeous image that was then added hundreds and hundreds of hours to the Hubble Ultra Deep Field, where people said, no, you're going to run out of galaxies. In this small patch of sky, 10,000 galaxies. And when we're looking for the highest redshift galaxies, when we went back in 2012 and gave 100 more hours, we found only 7 likely candidates inhabiting the universe within 600 million years of the Big Bang. So it's kind of like this needle in a haystack situation. But of course, we have all of these galaxies. So with all of these deep fields, you get access to basically galaxy evolution across, maybe not from present day, because it's such a small volume, but you're doing quite well from cosmic noon onwards. Now, when we are looking for these galaxies at high redshift, we use the universe to help us. We use neutral hydrogen in the early universe to help us. And this is just to show what happens to a galaxy spectrum as it traverses clouds of neutral hydrogen. This was actually a video that was designed to describe the Lyman alpha forest. So it's not quite for our situation, but I still like showing it. So as the light travels from the galaxy, the spectrum is being redshifted. And whenever it meets a neutral cloud, where there's a where it can excite that electron in the neutral hydrogen, it's going to absorb some light. And around about here, we've got where it can ionize that electron. So you start to lose the light, and that's because neutral hydrogen gets in the way. This is what has been used to make the Lyman break technique for identifying galaxies. It's not the only technique, but it is one that is been predominantly used. And if these are all of the filters that were available basically with Hubble, and each of these is an image that corresponds to one of these filters, this is a spectrum that's just going to be artificially redshifted. We're losing light here because there's more neutral hydrogen in the early universe. But what we see is we get what I call a cliff. It's not actually a cliff, but you see the galaxy and then you don't. So it's called a dropout. This is the feature that we look for, and often in the spectrum to confirm it, we look for this cliff here. And that can be enough for us to confirm it at high redshifts. So it's a simple technique and very effective. We would have liked to have been confirming these galaxies as we went, but it was incredibly challenging, partly because they were so faint, partly because the spectral capabilities just weren't there. These were some examples of spectra that got me really excited pre-JWST. This was the highest redshift spectroscopically confirmed galaxy. It's called GNZ11, and we see it later in this talk. And this was the imprint of the cliff from the Lyman alpha drop. That was enough in this smudge here to confirm it and make it an exciting spectrum. And this one was super exciting because it was emission lines of something other than hydrogen. There's carbon here. So Our information primarily on these objects was coming from imaging, not from spectroscopy. We weren't really learning a lot about the ISM at that stage, right? But we had some hints that we might learn a lot with spectroscopy. So we mostly had distances inferred from photometry using Lima break. They're called photometric redshifts. And then if we wanted to infer any other properties, for the deepest galaxies, Hubble, sorry, for the deepest galaxy, for high redshift galaxies, Hubble would be probing the rest frame ultraviolet. Our access to the rest frame optical, which we need to tell us anything about sort of the past of these galaxies, was given to us by the Spitzer Space Telescope, which was a pretty small space telescope. And it was the only thing that we had. And this plot is really nice because it shows you that if you have a young galaxy, young stars tend to have this sort of shape where we call it blue in the UV. They have a small Balmer break here. And that would be quite a young stellar population. And then as we add more and more old stellar populations, we get redder in the UV, we get a bump, a bigger Balmer break. So maybe these bands were all we needed to learn about the history of the galaxies. And to just show you the, yeah, I did have it. Basically, what we're looking at is imprints of stars with different lifetimes. So O-type stars with very short lifetimes, very blue all the way through, but A-type stars have a very strong Balmer break. So if it's old enough that your light is dominated by the older stars, you get an older Balmer break, basically. The thing is, this doesn't work at high redshift. It works in some cases, but it took quite a lot of persuading from some people that actually you have to care about the emission lines. And this was more of a problem than an advantage to us in the very beginning. We wanted to infer stellar masses, other physical properties, get beyond just sort of counting galaxies from their UV brightness. So this, yeah, it isn't only stars that emit in the rest frame optical. So this is a big problem. And this contribution of the emission lines, we just couldn't really disentangle it very well. Some people did some really great analysis, but people still went ahead. We knew of this problem. We addressed it by trying to model them. And we inferred things like stellar masses, because if you want to do galaxy evolution, you want generally something that links to your halo masses very well, and often that's a stellar mass. It's one of the most useful properties. So people were doing this and doing, these are now mass functions. I'm sorry that it's hard to read the axis labels, but it's stellar mass on this end, number of number density for given stellar mass in co-moving megaparsec cubed. So this is just one step beyond your UV luminosity functions, but it's easier to compare to simulations. And if you get a stellar mass and you've got some UV, you can infer a star formation rate. So people looking at how specific star formation rate, which is star formation rate of a stellar mass, might evolve with time. So it's quite cool that it was shown that it was increasing. In fact, early results were showing it was very flat, and that's because we weren't accounting for emission lines. And we were all in a pickle, and all the theorists were getting very excited, but it was just the emission lines. But that's really interesting in itself. So it's a higher star formation rate compared to the past integrated star formation in that galaxy. So maybe this is, higher gas fractions, more fuel, it's a higher star formation rate, maybe higher star formation efficiencies in high redshift galaxies. But there was a huge difference in the sensitivity between Hubble and Spitzer, and these are the two filters that gave us most constraints. See if, yeah, okay, the mic. And there was a huge difference in the spatial resolution. So if this is Hubble and then this was Spitzer, it was a small telescope. It was at longer wavelengths. It had low sensitivity, low spatial resolution. So the things that we could even do it for were just very kind of the brighter galaxies. But, you know, JWST is here now. Why am I even telling you all this? We've sold all of this, right? JWST is here. We've got near-infrared camera that pushes to wavelengths similar to what we had with Spitzer, but with very high sensitivity. And to go to higher redshifts, if we want access to the rest optical, we've got MIRI, which is also more sensitive than Spitzer. And the resolution is beautiful. So we're not getting into a confusion limit. We also have, rather than just 2 filters from IRAC, so this is the array of possible filters we can choose from in NearCam. And these 2 here are very similar to the ones we had access to with Spitzer. But we have all of these choices, including a lot of medium band filters, which then help us disentangle the emission line contribution to different filters. So even now with imaging, the fact that these rest optical lines are really impacting the photometry is a great advantage if we want to learn about ISM properties or anything else in these galaxies. And of course, we have beautiful spectra. We don't get spectra for absolutely everything, even with the GISM spectroscopy. That's hard for the fainter galaxies. These ones are from NearSpec, which does multi-object spectroscopy for, you know, a couple of hundred at a time. Now, whereas spectroscopic redshift was incredibly challenging before, you know, we're putting hundreds of these on a mask, maybe 20 of them per mask are above redshift 6 or so. We're getting very high rate of spectroscopic confirmations, but look at the gorgeous emission lines. I didn't even get to work on these emission lines at redshift 2 in my PhD thesis. My redshift 2 spectra looked as good as the redshift 6 spectrum I showed you at the beginning. These are actually the best spectra I've worked with in my career. You guys are probably in a much better situation, and I hope you are. But for us, this is amazing. So moving on to analyzing this rich data set, we've gone from sort of having very sparse data to having this incredibly rich data set, and we want to learn about galaxy evolution. We can do things now that we've got spectra, or even just with the images, we can infer things from emission line fluxes themselves, maybe star formation rates. When you're taking them from emission lines, they tend to be on a time scale of about 10 million years, and that's because that's about the lifetime of the cloud that's being irradiated by the young stars and producing the nebular emission. You can infer dust attenuation, maybe even the likely ionizing source. You've got metallicities, densities, chemical abundances. There's a whole wealth of things you can learn from the emission line fluxes ratios. I'm going to say see Danielle's talk because I'm not going to describe that here. But you can also go down the SED modeling route, and we can potentially infer all the above, depending on model complexity, as well as that really important property stellar masses, so that we can start putting things on a mass axis at the bottom. And we also have access to star formation rates over longer timescales, and that's because our star formation rates, when we take them from the UV, those stars can live longer. I mean, some people say it's 100 mega years. It's not. 100 mega years if you've got constant star formation. You get a rapid variation in the UV as well as young stars die. But still, it's longer timescales usually than the emission lines. So before I move to telling you a little bit about SED fitting, because I'm guessing that quite a few of you here have not used SED fitting. I know that some that I'm working with have not done it till this week. Were there any questions about the anything that I've shown previously? If not, that's great. I'm just going to assume that it was low enough level that, you know, you're following me. Good. So I will ask that again after I've described this. So if something's not clear, I can take you back and just describe it a little bit better. These are some of the SED fitting codes. There are actually many more. These are some that are being, you know, predominantly used Europe even for JWST data. There's kind of 2 things you have to care about with SED fitting. On one side, well, basically what it is you're comparing models to data and you're inferring some physical properties. So the first side of this that we talk about is the models, what's going into them. And they are complex. So this is from a review in 2013. And if anyone and someone who's doing more of this, I really encourage anyone to start there. We have to build kind of galaxies of stars. And we start with a basic building block, which is a cloud of gas and dust of a given properties has collapsed and formed stars. And we assume all of those stars have the same metallicity and are now going to evolve on their basically tracks, their evolutionary tracks, which is based on their mass and chemical abundance. The distribution of masses that we had in the beginning from that cloud is described by what we call the initial mass function, where there are many, many more low mass stars than there are high mass stars. And then once we've done that, at any point in time that you want to look at this, what the stars look like in this cloud, you take all the stars on their evolutionary track at that point in time, and then you want to assign them each a spectrum, which come from libraries of templates. That will give you a spectrum for all of the stars that have formed from this cloud. But we know that a galaxy is more complicated than a single cloud, so you have to take into account now all of the clouds that have formed over time. It's likely that, they're going to change their metallicities over time, but a lot of the SED fitting methods don't vary that. They have a flat metallicity over time. And we have what is called a star formation history. And these can be as simple as this galaxy has been forming stars at a constant rate since it started. Now we're going to build up what we think that looks like. It doesn't matter that that's not physically possible. Like, this is one of the analytic forms that is still used. And you can be arbitrarily complex in this, but generally simple forms are used, or you might bin in time. And then once you've done that, you have what you think your stars look like for your whole galaxy, and you have to add in your dust attenuation. This is generally done that latter stage, although there are models that take account of different distributions of dust, some dust in the birth clouds, some dust that's diffused throughout the galaxy, and then you get attenuation and emission. Those are the basic ingredients. But there's a big thing missing here, which back in 2013 was not included, and that's the nebula models. There's no emission lines, and there's no nebular emission at all, which is why we were getting things wrong in the beginning with how the specific star formation rate evolved. So this was a big effort that was sort of put into motion because of the Spitzer data, but also because we knew JWST was coming, and we knew that we had to improve things. Now we simplify. We have to simplify the galaxy. We can't add in all the complexity necessarily. So if this is a star-forming region, an H2 region, so one of those single birth clouds, it's got beautiful complexity. It's got changes in distribution of dust and density and everything else. And we treat it as basically a sphere. It's done with 1D models using radiative transfer using Cloudy. People are improving this, this modeling technique, but this is the basic one. And then this will be done and modeled what the light passing through the H2 region with a large grid of physical parameters for the birth cloud itself. So the metallicity of that birth cloud, the density of electrons there, all of these sorts of things. We'll vary them so that we have a big variety within the models, but we're not varying sort of the structure at that level. And then we have these beautiful galaxies. We have many different H2 regions. It's gorgeous. They're all going to have different properties, but we simplify the galaxy in SED modeling that, well, okay, so we're going to add in lots of different H2 regions, but they've all got the same property, and we're hoping that we're sort of describing a typical property. So this can be dangerous, but it's a good first step. So this is our galaxy. It's got H2 regions, it's got stars, we can put the spectra. We now also add in there's continuum emission from these H2 regions, and there is emission lines. So we can add them into our modeling. And what we introduce now when we are modeling is that we introduce some parameters that describe the physical conditions of these H2 regions. Those star formation histories, I said that some of them are very simple. This is a huge area at the moment where people are trying to improve things to make them arbitrarily sort of peaky, or being able to describe more complex scenarios. I'll explain why that's needed. And you can add in other components here. So we've mentioned stars, we've mentioned dust, we haven't mentioned AGN, and they have a huge impact on the, especially the emission lines. So we've got Beagle AGN includes the narrow line region. So we just say, well, okay, you've got a spectrum. You can generally tell what the broad line region is, but you can't always disentangle the emission that's coming from the stars, the H2 regions, and the narrow line region when you've got very small galaxies that you have integrated light. It's easy when you're at low redshift and you can start to look in a 2D way. And then there's also other parts of the AGN emission that might be added, like dust from the hot torus, etc. So those are the models that go in. They introduce quite a lot of free parameters that we then want to find the best parameters that fit to our galaxy, but we also want to understand how uncertain they are. Now we need to compare them to the galaxies in a quantitative way. Minimizing chi-squared is one method, where it's the observations minus the model. This is photometric fluxes here, but it could be the pixel by pixel spectra. And here's the uncertainties on that. A lot of these SED fitting codes, though, they work in a Bayesian framework. And in a Bayesian framework, you create a likelihood. And rather than minimizing a chi-squared, you maximize a likelihood. I mean, it doesn't really matter in some ways about what the nomenclature is. The way you go about this is you think about how are my errors distributed. If you think your errors are pretty much distributed in a Gaussian way, then construct a Gaussian likelihood. And if you think your data points are independent, then you can just be doing a product between the two. And if you think they're correlated, you have to take account of that correlation. But often when we're doing at the simplest level, we're assuming they're independent data points. And this is what a Gaussian likelihood looks like. Again, here's the observation, the model, and the uncertainties. If you take the log of this, it doesn't look so different from your chi-squared. Where you care about it is in the fact that it's a full probability distribution function that has the right normalization, so you can use it as a probability within that framework. And then what you want to learn is you want to learn when you're comparing your models to the data, you want to learn what is the probability of my model given the data. But what we have is the probability of the data given the model. This is what the likelihood gives you. And so with Bayesian, with Bayes theory, we can transform that to what we want, and we use a prior, which is the probability of the model, and we divide by a normalizing factor, which is the evidence. Often people don't worry about the evidence. The evidence is really useful when you have different models. So let's say I've got an SED fitting tool that has H2 regions and it's going to fit H2 regions. And then I've now allowed it to also fit a narrow line region component. I can compare how well they have done using the evidence. The priors often are uninformative, but there's becoming more and more reasons why we need informative priors. And actually, that's one of the, sometimes something that people worry about is the prior. You want to always compare your posterior to the prior to see how much you've learned. And sometimes in SED fitting, people haven't done that. But being able to adjust this when certain things are poorly constrained based on physical intuition is incredibly powerful. You just then have to worry about whether any of your questions are circular, because maybe you're setting a prior based on some simulations and you want to compare your data to those simulations. You have to be careful at that level. So that's kind of a whistle-stop tour of SED fitting. That's how we construct the models and then how we're comparing the models to the data. That can be at the spectral fitting level, that can be at the photometry fitting level. So before I go on, are there any questions? Is there anything I haven't explained well, or just like, maybe you zoned out on that slide and you're like, hang on, I just wanna, like, you, even if I'm repeating myself, it doesn't matter.
No question.
So these assumptions that the SED fitting models are making, do they hold when you go to regions where you know the complexity? Do they like prove good assumptions? Or like if you take a chunk of a galaxy and you try your fitter there and you try to fit a different part of the galaxy, does it infer, like give you similar information?
So different part of the galaxy, I would love to have more of my observations that are probing different parts of the galaxy. I'm often stuck in MOS mode rather than the IFU. But even in MOS mode, no.
And the other question I had, is there an SED feature that deals with the AGN and the stars at the same time?
So different levels of AGN, yes.
Okay.
So the AGN narrowline region, just the emission. Beagle AGN does the line emission and disentangles that.
Cool.
Yeah, but it doesn't include the dust emission at longer wavelengths. Other tools often including the dust emission at the longer wavelengths for the AGN component. So then you have the star forming contribution to the dust or the AGN contribution to the dust and can disentangle that. But yeah.
Other questions?
Okay, no problem. Also, I'm like happy to answer anything or talk about any level of this at any time, like that you see me through the week. So I'm kind of a bit of a geek when it comes to SED fitting. So no question too simple or anything like that, don't worry. So now we have huge amounts of data from JWST. We have like some nice models that are at least going to account for our emission lines. Like it should be easy going now, right? We should be able to get our stellar masses. We can plot lots of different properties against each other. We're going to compare to simulations and we're going to understand galaxy evolution. Well, we're starting. So whereas people were measuring stellar masses before with Spitzer and making stellar mass functions, they were assuming constant star formation history. There was so little data that they couldn't constrain complex scenarios. They had to make the scenario so simple to be able to get a stellar mass out. Now those can be relaxed and more complex star formation histories can be employed. So people are measuring stellar mass functions with more physical assumptions out to high redshifts and sort of, yeah, there's nothing like particularly worrying at this level. People are looking at relationship between stellar mass and star formation rate. So one would hope actually at this level that we were doing maybe a little bit better than this in going to lower masses with JWST, but we see that there is some evolution where it's the normalization of this is increasing to higher redshifts. And this also reflects that increasing specific star formation rate that I showed you earlier on. And that's kind of in agreement with what was seen before. So doing reasonably well, even with simple assumptions. So these are the things that are kind of working at the minute, but there are some strong caveats. Looking at the mass metallicity, we see strong evolution. So these are color coded by redshift. So from yellow, redshift 3 to 6, and blue is 6 to 10. And this is the local galaxy sample from SDSS. And these are the bins from JWST. So we're pushing to lower masses and definitely seeing a strong evolution, not just in how much lower they are in metallicity, but also in the slope. So that's something that we just couldn't do at those redshifts previously. That is a lot easier now, but there are still some assumptions there that we have to address. But one thing that we see that came up pretty early, which is really beautiful and clear, it's just a simple, clear thing that you can see. If you get a population of galaxies and you get spectra from them, they are diverse. Some have strong emission lines, some don't. And it's not just about whether they have emission lines or not that's interesting. This one here shows a Balmer break. This one has recently stopped forming stars. That's the best interpretation of this spectrum. It's napping, it's having a nap. Whereas this one is probably in a really bursty phase, going for it, but maybe these are part of the same population where you can have a burst of star formation and supernova in a certain region go off and dispel your gas from that region. You remove the fuel for star formation, and you could, for a short while at least, quench your galaxy. It's not quenching in the true sense. It's going to start forming stars again. It's not quenched forever, but it's mini quenched is what we've decided to call these. And what this is, a very clear indication of stochastic star formation histories. So I told you that they were being modeled as a very simple analytic form. That would be really nice because it's quite easy to do stellar masses and stuff like that. This messes up things quite a lot. Yeah, so it would be a very jagged star formation rate with time. So you'd have high star formation rate, low, higher, low, higher, low. Not necessarily oscillatory. Bursty, bursty. Yeah, definitely. So now, when we're trying to do simple things like our stellar masses, these are with technically different models. So I say it depends on your priors, but it also depends on your models. So what are your underlying assumptions for how you think the stars are evolving? These are a big difference if it's hard to read the numbers here. Imagine moving them by sort of 0.3, 0.5 dex, which is not very comfortable. Okay. Also, the highest redshift objects have us really puzzled. If we go to the highest redshift objects, this is the age of the universe. At the top, you can see the redshift. We've got some objects marked here. This is a line that's really pretty easy to explain. And it's kind of taking the halo mass function at a certain point and converting a certain amount of gas so they should have into stars. And then you can explain the brightness very easily. These are our observed galaxies, which are lying above this. So very early on, this was kind of pushed. I was skeptical because one of the first candidates for this that was going to break the universe turned out to be at redshift 5 rather than 16. So I thought, okay, let's just wait for people to get their confirmations. And then another very luminous object, I'll tell you about in a second, had other reasons we thought maybe this is not a problem. But more and more of them we're finding, and again, they are diverse. Some of them are showing you strong emission lines, some of them not so much. And one of the many explanations, to try and go through them is a completely different talk and not the point here. One of the explanations that people are suggesting, or pretty much all of them, rely on them having to be in one of these bursty phases. So if their star formation rate is much, much boosted compared to what it was previously. Sorry, I didn't mean to go through all them again. This is another imprint of it in the UV luminosity function. So I showed you UV luminosity functions, which were just nicely evolving and increasing in number density with redshift. But what they were seeing is that as they were pushing to higher and higher redshift, they weren't dropping the way that they were expecting them to. So this is sort of like redshift 11 and above. So that's another way of saying that our very high redshifts are more luminous than we're expecting, and we can't explain with simulations currently. And this was a plot to show that some people are evoking the stochastic star formation histories. And one probe of this might be to look at star formation on different timescales, on 10 megayears compared to 100 megayears of these luminous galaxies, and see whether they might be in a bursty phase or have had a higher star formation rate right at the moment that we're seeing them. Can we somehow learn about what's going on then by probing their ISM properties, probing their abundance patterns? There's something really interesting coming out from these spectra as well. You saw some of them had really strong emission lines. This guy actually is not one of the superluminous ones, but does show strong carbon lines. This one here, the peaky one, is C3. If we put this is carbon versus oxygen. We've inferred this both from SED fitting and from different estimates. And it looks to be supersolar carbon over oxygen. Can we be trying to disentangle what's going on with these galaxies based on comparing to what yields we might expect from different populations that we would get at these redshifts? That's might be a nice way to probe it. So if it was by these estimates, they kind of sit on possible yields from population 3 or that first generation of stars. So maybe we're seeing some boosting in carbon to oxygen from the first generation of stars. But it doesn't necessarily agree with what we get from SED fitting. And this guy, this is GISM3 again. This was the highest redshift spectroscopically confirmed galaxy pre-JWST. It was that smudge. And turns out it's not a redshift 11, it's 10.6. It's got gorgeous emission lines everywhere. It was shown in almost every talk that year, and I think still gets a show in most of them. It's got really strong nitrogen lines. So even just looking at it, it's got strong carbon lines as well. There's possible evidence that it hosts a black hole. So this was another possibility for why our highest redshift galaxies were luminous. What if some of that light is coming from an accretion disk around a black hole rather than from stars? Then we don't have to explain it with stars. And this evidence came from looking at density estimates from nitrogen lines and finding very, very high densities and saying, look, you're not seeing them very broad, but I think you're seeing a broad line region. I think you're seeing a narrow broad line region because this is such a low mass black hole, like about 10 to the 6 solar masses. But a subsequent spectrum in the rest frame optical, if that was the case, we might expect to see a broad line in H alpha, and we don't. So the jury's out on this one. But it does show very strong nitrogen lines. We can go back to this. And well, with some assumptions, this might indicate a high nitrogen abundance. There are many other objects indicating something similar. This object here, you're just seeing them. Here's C4, here's C3. This one doesn't have a super high carbon over oxygen, but has high nitrogen over oxygen. We can't rule out the presence of an AGN because there are some very high ionization lines. The thing is, with nitrogen over oxygen, when we look at local objects, they follow this type of relation. So here we've got primary nitrogen synthesis, and that's at low metallicities, but once you've got enough oxygen, the amount of nitrogen can also be dependent on the amount of oxygen that was already available, and that secondary nitrogen synthesis But here are our high redshift objects completely off somewhere else. Are our stars doing something completely different? Are our yields from our early stars doing something completely different? In which case, all of those assumptions in the SED fitting for the early ones get broken. So people have investigated different IMFs. That was one of those inputs into SED fitting. Do our early stars, because they form without much cooling of the gas, they're forming without much fragmentation of the clouds, they're really massive. We don't get many of the small stars. Maybe this can produce these abundance patterns. And it is suggested from some of the evolutionary models that that could be the case. But again, only recently, early this year, another study came out and said, look, guys, you're doing all this stuff. It's great. You're publishing tons of papers really quickly. Have you thought about the densities? So those nitrogen lines that we use in the REST UV come from a different region, generally denser regions. They're very high ionization lines than N2. Which we tend to use for at lower redshifts for nitrogen abundances. That's what we get from these guys. If we're assuming densities that have been measured from lower ionization lines, or just assuming some standard density, we might be getting these abundances wrong. And if they found some galaxies where they could estimate the densities and did these abundance estimates with higher densities, it was starting to fall on the local track. So maybe in the end, the abundances aren't going to help us that much. We have to care more about the conditions of the ISM before we start trying to infer our chemical abundances. This is a big plot, and I'm not expecting anyone to be able to read all of these. This is an output from Beagle. This is a new spectrum, which I thought was on arXiv this week, but I guess it's not out yet, where we have, again, strong carbon lines. And there was a hint of helium-2, which is quite high ionization, not super high ionization. You don't necessarily, but it's not well produced by many of the cloudy grids. But we've fit it with and without the narrowline region contribution to see whether we required an AGN to reproduce these emission lines or not, and we don't. Like, the evidence doesn't really favor it. And that's that Bayesian evidence that we can use to compare different models. But it does require an enhanced carbon to oxygen abundance, whether it's produced by the narrowline region or the star-forming region, and whether we allow for higher densities. So maybe some of these abundances are robust and we can start interpreting, but still these are with assumptions in our model grids. So this galaxy, rather than being sort of where the previous one was, by our estimates, is sitting right within the yields from population 2 stars or the second generation stars. So a bit less interesting maybe than possible population 3 yields. So, I mean, I come to a summary, wrapping up very quickly from all this. I've just kind of unpacked it, and every level I've said, well, okay, but maybe not. We're getting there. People are doing this. And I said, how do we want to study galaxy evolution? Gosh, I'm finishing far too early. What happened? Okay. How do we study galaxy evolution? Often we look at some properties of the galaxy population, brightnesses, masses, amounts of metals. So we need those properties, and we can compare them to simulations and infer the physics that's going on. GWST is bringing dense SED sampling, so we can disentangle the emission line contributions. It's got spectroscopy, and it's going very deep, so we can look to fainter galaxy populations, higher redshifts. But at the moment, thankfully in some ways, because I'm glad that it's given us some very interesting puzzles to chew over, Stochastic star formation histories make all of this challenging because that basic physical property that we might like to obtain, stellar mass, is incredibly challenging. We can't actually constrain a star formation history from some photometry data or even from a spectrum because it is generally dominated by your youngest stars. So at the moment, we're having to go with informative priors. So we might assume that they have to increase in their star formation rate over time. That's a very simple one. Our basic observed properties even. Let's take a step back and forget about determining stellar masses. Let's just go back to the UV luminosities. They should be fine, right? Because, we've been doing that for years. Theorists have been working with our observation for years. And we can't describe the most luminous high redshift galaxies from the simulations. So this is great fun. We're loving it. But, it does mean that we're taking a step back before we take a step forward. We're kind of rushing to get all of our models and calibrations more suited to the very high redshift universe. And there are low redshift analogs, and I'm hoping that Danielle will tell you more that help to guide this. But at a certain level, you're never going to have a low redshift analog that is being illuminated by current population 3 stars that are supermassive, et cetera, right? There are certain things that you cannot reproduce locally. But we are seeing unusual chemical abundances. Maybe they are robust. Maybe it's the ISM conditions that we have to care about. But maybe we can make a lot more progress even with allowing the models to also constrain the chemical abundances, et cetera, to understand what our stellar populations are doing and constrain more our stochastic star formation histories. So yeah, I'm surprised I ran through it so quickly, but I'm ready for questions and ready to talk through with any of you on any other day about any of these results. So I'm super happy to have discussions afterwards.
So any question?
Hi, this was a really cool talk. I love hearing about this high redshift stuff. Could you explain more how we know from the spectrum that the galaxy is like napping?
Yeah. I should have just come out of the thing, right? So normally when you're getting rid of emission, sorry, I'm thinking in terms of like when you get your models and you want to reproduce the spectrum with SED fitting or something, you can get rid of your emission lines by having a high escape fraction. So you say that you're ionizing photons that are ionizing the H2 region. They're actually escaping from the clouds. That's really useful because we want them to escape to ionize hydrogen in the universe. But what that would do is that would leave you with the imprint of the young stars. And they don't have a strong Balmer break. The only way you get rid of the emission lines and you produce the Balmer break is that you have to have had those young stars die off so that you're starting to see the luminosity contribution from the slightly longer lived low mass stars, which do show the Balmer break.
Thank you.
Yes. The property of the ESM are probably completely different at these times. So first, redshift of 15 is what age?
Redshift 14.44 is like, 16.6 was 230 million years. Redshift 14.3, you're getting to like 300 million years. So.
And at this age, what is the temperature of the CMB?
I don't know the exact temperature, but it's true. So you expect that it should be still warmed, but except when you've got quite dense clouds where the stars have formed. By that point, maybe they're
40, 50.
Thank you.
Not so large. Okay. And then, what are the scenario to form stars, very massive stars, so quickly?
So quickly. So now it's not so much that simulations need to form them more quickly. It's that simulations were a bit too simplified in converting halo mass to a UV luminosity. So you don't necessarily have to have them forming earlier. You need them to be brighter. And that can be some...
Heavier also then?
Sorry?
Heavier? But if they are
No, they
brighter?
don't have to be heavier because this is from the rest frame ultraviolet. So you could have more massive stars at the top end of your IMF. So if often with the SED modeling, we might cut at 300 solar masses, but if your POP3 generations are going up to sort of 500, 1,000 or anything like that, you have to get rid of dust. And that might sound crazy that we're forming dust so early, but people are, from ALMA constraints, we get early formation of dust. So Andrea Ferreira says, you've also got to get that dust out of the galaxy because that's going to even get in the way and not make them bright enough. And so if you can have radiation-driven outflows from a star formation burst event, that will work. And then this other scenario is saying, well, what if the gas is collapsing so quickly that you don't have feedback? And they call it sort of feedback-free, but it's not quite that. It's a density modulated, so that you have such rapid collapse that you can form more luminous, massive stars that way, because you're not getting the feedback from the radiation on the, it's just a faster time scale.
And so you just mentioned ALMA. So those galaxies or high redshift galaxies has been observed in the millimeter or submillimeter?
Yes, so I've not shown those results for this one, but even the GSC14, this one's got ALMA constraints, has been observed in ALMA with an emission line.
Detected or
Yeah, detected.
First, thank you for your nice review of results. So more than a question, I have a comment regarding the nitrogen over oxygen ratios, because, you know, everybody jumped and tried to explain with models these crazy abundances. As you said, maybe they are not crazy at all. And I fully agree with you that we should be very careful about the peculiar physical condition of the gas at this high redshift. What I wanted to point out, I think is really important, is that in the comparison of these abundances, we use discrete grids of yields, just because people running stellar evolutionary models can just run a few models.
Yes.
And in particular, nitrogen abundance is boosted with high rotational speed of the star.
Yes.
And at present, we have a few models for rotating massive stars, and the results are not in agreement. So I think this is a field that has to be completely studied and investigated in the future. And also stellar binarity, because people doesn't consider that enrichment by massive stars in binaries can
exactly
change.
Yeah, also Chiaki Kobayashi explained the possible nitrogen abundances in GNZ11 with Wolf-Rayet yields, but she's also saying, like, be careful of the Wolf-Rayet yields, they're not quite ready yet. And so, yeah.
Any other question?
So you said that for some of these galaxies, you had some ALMA detection, but yet when I look at your stellar SEDs, I had the impression that you almost don't have any attenuation. So in your SED fitting, do you account for some sort of attenuation? And if yes, do you have an estimate of, the column density of dust in these objects?
Okay, so we don't estimate the column density directly. In the past, in SED fitting, an energy balance has been used, which is saying that any of the dust seen by the stars, the energy that is attenuated is then what's going to be re-radiated into your far infrared. The thing that we see at high redshift is that we will see UV clumps in the galaxy submillimeter clumps, and they are offset. So energy balance may work on a sort of resolved 2D scale, but certainly doesn't work on an integrated galaxy scale. So even asking for the small attenuation and saying, well, what does that predict? You can't do it from the bit you're seeing in the UV necessarily. It could be that the dust is coming from completely obscured star formation.
Okay.
So maybe it's a question for the roundtable, which, by the way, everyone should join the channel. But what would be the input that you would most want in order to help interpret these observations? Would be from stellar evolution models or from cosmological-like simulations? And flipping the direction of this, what would you most want simulators to try and incorporate in the models most?
Getting to higher resolutions such that being able, like Harley Katz is doing, so there are simulations where you're starting to resolve somewhat the ISM and its complexity. And so that means that when you are comparing, you're comparing apples to apples. When you get an emission line, you have the varying contribution of it from different density regions. Also including binarity right from the get-go and associating that with the yields, but also with the feedback from supernova, et cetera. So this is kind of sounds like a crazy wish list, and it's something I've been talking with a colleague about, like how far can you go with incorporating these? And I think it's now it's possible for galaxies that would resemble the very high redshift ones because they're quite low mass and you don't have to run the simulation till redshift 0. So I personally would be wanting higher definition of the ISM, feedback from the stellar physics, and also proper incorporation of AGN because we're seeing their impact and we're often on a resolved level.
So I think we can speak again. We can thank again our speaker.